The first thing in section 6.4 is graphs of log functions. And I figured this would be a little more effective to really kind of show how you get the inverse of an exponential. So I guess the only real base I could use here was 2. Otherwise, the graph just gets too big. So even though this is kind of the exact same thing that's in the book, otherwise you get things that are kind of impractical to graph because even if I used base 3, I'd end up with a y value of 27. So that's a little tough to graph. But in any event, the blue one, or which it doesn't really look blue, but that's what color it was when I wrote it. I think the scanner turned it almost black, or maybe like a deep dark blue, whatever that is. That one is an old one. It's from section 6.2, I think, where that's an exponential function. That's y equals 2 to the x. And then there are its points, right? If you raise 2 to the 0 power, you get 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And then going the other way, 2 to the negative 1 is 1 half. 2 to the negative 2 is 1 fourth. 2 to the negative 3 is 1 eighth. And you have a horizontal asymptote here of y equals 0 because there's no number that you can raise 2 to and end up with a 0. And there's no way you can get a negative either, right? I mean, you can see it here, right? Like if you raise 2 to a negative power, you get little tiny numbers. And if you raise 2 to a positive power, then you're on the right side of this graph. So you're not getting any negatives anywhere. Then the graph of the log function with base 2, this is the inverse. So you could just flip the x and y coordinates to get the points. But if you think of it as that the log is whatever power you'd have to raise 2 to in order to get x. So you have to raise 2 to the negative third to get 1 eighth. You raise 2 to the negative 2 to get 1 fourth, right? 2 to the 0 gives you 1. 2 to the first gives you 2. 2 cubed gives you 8, and so forth. But yeah, to get the points, it is basically you just interchange x and y. But that's how you graph an inverse, generally, right? So the red one is the new one. That's the log graph. And most of the log graphs that you're ever going to have to like think about or draw or anything, they're going to be this kind where the base is greater than 1, where then it goes through 1, 0, and then you've got this vertical asymptote right here, the y-axis, so x equals 0, and then on the right side it just goes off like that, increasing. Usually it's that, but every once in a while you get this. So this down here, number 2, the only difference is that now you have a base that's less than 1. So 1 half, definitely less than 1. So this graph looks reversed compared to the one that's up on top, right? Compared to 2 to the x. But there you still got the horizontal asymptote, the x-axis, right? You can't get negatives, you can't get 0. But then the red one, the log function, again, that's the inverse, right? I guess it's not as easy to see here, but I guess if you sort of tilt it mentally so that that dotted line, that dotted y equals x is like going straight up and down, then you could see it, right? Because then if you combine the two shapes together, it's a mirror image. So like it's still there. It's not as obvious as it is in number 1. It's not as nice looking, but it's still there. In these you do see occasionally where if you do have the graph of a log function where the base is less than 1, then still going through 1, 0, right? That's always part of this. It's just that now if the base is less than 1, then you have this part that's approaching the vertical asymptote up above instead of down below. And so then consequently the other piece goes down below and is gradually decreasing. Lastly, on this page, since we talked about how in the calculator you really just have a base 10 log and then natural log, if you want a different base, like a base 2, like the ones that are here, you'd have to graph one of these things. So you'd have to do that change of base conversion that's in the last section. But if you do this, like if you graph log x divided by log 2 or ln x divided by ln 2, your calculator should handle that if you got a graphing calculator. So realistically, the base that you might have to deal with the most often, probably going to be natural log, probably going to be base e. So what about graphing that one? And it's a little tougher if you have to plot points. I mean, you know 1, 0 is going to be on there, but then like e1, right? Because if it's base e, you raise e to the first power, that'll give you e back out. And then the natural log of 1 over e ends up being -1. So I converted those into decimals. So e is about 2.718. So then 1 over e is about 0.368. So there's the 0.368 -1. Then there's the 2.7181. And there's the 1, 0. And it's going to generally have this shape because e is a base that's larger than 1, right? It's 2.7 something, like it says over there. So you get a shape that's pretty similar to what you would get for the graph of y equals log base 2 of x. And you still get that vertical asymptote at x equals 0. And with base 10, you kind of end up with the same thing, except that a couple of x coordinates are different. So like how here, like there's the base, right? There's the e, and then there's the e. If you use base 10 instead, you're going to have the points 10, 1 and 1/10 -1 instead of e and 1 over e. So yeah, same overall shape. I guess this would be tougher to graph just because you have to stretch pretty far out to get that x coordinate, but it's the same idea. And toward the bottom of this page, the shifts and things that we used to have back in chapter 2, those could be applied to the log functions and exponential functions as well. So here, instead of the natural log of x, we have the natural log of x plus 4. And remember back when we would do this with parabolas and square roots and things, if you had a plus, so like if where usually you'd think there would be an x, or it was like an x plus 1 or an x plus 2 or an x plus 8 or whatever, then if you have the plus, that's a shift to the left. So x plus 4 is a shift 4 units to the left. So the natural log function had a vertical asymptote at x equals 0. That's shifted 4 to the left, so now it's at x equals -4. You can kind of see that dotted line in there. And then all the points are going to move over as well. So instead of 1, 0, you have -3, 0. So subtracting 4 from the x value. Then e minus 4 is about -1.282, and then 1 over e minus 4 is about -3.632. So I just plotted those 2 points, and it's the same shape, just move 4 units to the left. Then this one over here, if I go up for a second just to see what it is, it's e to the x minus 2. So the e to the x graph, that would be in section 6.2, I believe. But it's that just shifted down 2 units. So instead of having a horizontal asymptote at y equals 0, that's also going to get shifted down. So now that's at y equals -2. And then the points are going to get shifted as well. So y equals e to the x would just have 0, 1. So you shift that down 2. That's now 0, -1. It would have the point 1e, but now if that's shifted down 2, you get e minus 2 for the y coordinate, which is about 0.718. And then instead of 1 over e minus 2, you get -1.632. And then same shape as the graph of y equals e to the x, or y equals 2 to the x, right? Anything where it's an exponential function where the base is greater than 1, right? They all kind of have the same shape. But then just shifted down 2 because we had e to the x minus 2. As far as finding domains is concerned, this is the whole thing right here, that log functions are only defined for positive values. Think about it this way. So I stuck in a specific base here. There's no value that you can raise 10 to in order to get 0. You can get really little positive numbers. So like if you had like some negative number that had a giant absolute value, like you had 10 raised to the power of -500, that's going to be a little tiny number that's very slightly positive, right? It's just going to be a little bit above 0. But you can't get 0. There's nothing that you could sub in for x that will give you a negative either. So the consequence of that is that any log function, so it doesn't matter what base it is, base 10, base e, base 2, base 12, whatever, undefined for negatives, undefined for 0. So then if you have any log function, you're trying to find its domain, you need the thing that you're taking the log of to be positive. So here, the log of x minus 4 has got to be positive. So you need x minus 4 to be greater than 0, but in order to get that, you need x to be greater than 4. So that's the domain, right? Just rewrite it as an interval, right? It's all values that are bigger than 4, strictly bigger than 4. So you end up here. This one, you would need 2 minus x to be positive. Okay, well, if I add x to both sides, I would need 2 to be greater than x, or to rearrange the order so it's easier to write the interval, x less than 2. So all values less than 2 would be that interval, right? -infinity to 2 and parenthesis around the 2 because we don't want to include that. Same ideas down here, but I guess these are a little bit more involved. Here, you need x squared plus 1 to be positive, but that's always positive. Right? As long as x is a real number, we're not talking about complex numbers, which here we are not. So yeah, that's always going to be positive. You don't have to worry about anything. Any value that you put in for x should work, right? Because you would need x squared to be greater than -1, but that's always going to happen, right? You square 0, you get 0. You square anything positive, you get something positive. You square anything negative, you get something positive. So yeah, those are all bigger than -1. So that'll work for all real numbers. So the domain should be all real numbers, so negative infinity to positive infinity. This one, this is a little bit more drawn out because you need x squared minus 2x minus 35 to be positive. But that does factor. And then this becomes something like in chapter 4, where you got to see where, or maybe not even chapter 4. It might go back a little bit further to where we had parabolas, I guess, since this one is degree 2. But this idea also does show up in chapter 4, where you factor the polynomial as far as you can, and then you have the number line and you test every interval. So that's basically what I did here. And I said, well, we get to use 0 because it's in between -5 and 7. So you do a test of 0, you get -35. All right, negative in there. Then -6 for this interval out here on the left for less than -5 for that interval out there. So you sub in a -6, you get 13. Okay, that's positive. And then 8 for this one out here for bigger than 7. You sub in 8, you get 13. That's also positive. So you need the two positive ones. So less than -5, greater than 7. Both of those intervals should work. So that's why I've got this union here of all values less than -5 and then all values greater than 7, just written out in interval form.